Hi, it is a review for exam number 3. This review will cover sections 3.7 to 4.4. Okay, here, let's see number 1. Use implicit differentiation to find equations of tangent line and normal line to the curve. Okay, the curve is given implicitly. In fact, this is a circle of radius 5 and at the point -3 and 4. So already point is given. So if we want to find the tangent line in point-slope form, then we have to find the slope, y prime. Okay, let's do here implicit differentiation. If we apply x derivative, then that'll be here 2x, and y is a function of x, so that by using chain rule, you make a derivative with respect to y and y x derivative, and right hand side is constant, so that the derivative is 0. Okay, from here, now y prime equal minus and x over y. Once here x is -3 and y is 4, then the slope must be 3 over 4. So that the tangent line becomes here, now y minus y0, which is 4, equal the slope 3 over 4, and x minus x0, x minus -3, which is +3. So that is tangent line. And normal line, here the slope must be the number such that the product with this slope is -1. So you can easily get the slope for normal line must be -4 over 3. So here we have the same point, so that y minus 4, and slope is only the difference, and 4 over 3 minus 4 over 3 and x plus 3. Okay. Now number 2. Okay. Now derivatives of inverse functions and logarithms. Okay. Now part A, fx is given in this way, and when x is larger than 1, then this function is 1-to-1 and it has its inverse. Now we try to find inverse derivative at -3. Okay, when you try to solve the problem, you have to consider this one. Main idea around it is that f inverse prime is same as 1 over f prime. But now the evaluation point must be well chosen. Now here the point is -3, but if you try to measure f prime at -3, then it's wrong, even f is not defined at -3. Pictorially, we can explain this one in this way. Okay, here domain and range of f, then here f inverse is defined on the range of f, and now we want to get the slope of f inverse at -3. So you have to find the corresponding point on the other side. Okay, let's say this is x, such that you have to measure f prime at the point and take a reciprocal. So we have to find this point. What is this point? Okay, that means that f of x equal -3. What is f of x? That is x squared minus 2x minus 3. That is f of x equal -3, which implies that there's x squared minus 2x equals 0, so that we have x equal 0 and 2. But for f, the domain is larger than 1, so that only possibility is x equal 2. Okay, 0 is not in the domain. Okay, so we found the point here, so that we have to measure f prime at 2. Okay, now what is f prime? That is, from the given equation, you can get easily that is now 2x minus 2, so that f prime 2 equal 4 minus 2, which is 2. So here the final answer is given in this way. The prime at minus 3 equals same as 1 over f prime at 2. That is same as 1 over 2. So 1 over 2 is the final answer. Okay. Okay. Now part B. Okay. Now the function is given along with power. Then when you try to find derivative, then you may use logarithmic differentiation. So here now, for given, okay, y equal x to the x squared, then logarithm of y equal same as, okay, logarithm of natural logarithm and x to the x squared. X squared is power, so by using power law, we can write here x squared times logarithm x. Okay, now we apply x derivative, then here that is y prime over y, and right side by using product rule, you can get here 2x and logarithm x plus x squared times 1 over x. So that is same as 2x logarithm x and plus x. Okay, so we can reach it here now, y prime equal y times of that one. What is y? Y is x to the x squared. So that here x to the x squared and times that one. So we can, if you can do here now x, the factor out, and 2 logarithm x plus 1. Right? Okay, that's the final answer. Okay, and number 3, delegated rates. A cube's surface area increases at the rate of 72 inches squared per second. So surface area is increasing a constant rate and of 72, and the unknown we have to figure out is the rate of change in volume, and particularly when the edge length is 3. Okay, now once we are considering a cube of length 3, okay, that is x, and also height is x. Then the surface area, S is the same as now 6x squared. Each side has area x squared, and there are 6 sides. Okay, now the data is saying that rate of change is now 72. So that we'll use that here as prime. Of course, prime is time derivative, and that is 6 times 2x and x prime. Here we are making time derivative, so that is 12x x prime, which is 72 in the data. That means that x prime equal 6. Okay, so here when x equal 3, you can specify x prime is 2. So you can get it, but you may use this quantity together later on. Anyway, now what is volume? We have to find out the rate of change in volume. volume is x cubed. X is a function of time, and so that also volume is a function of time. So we are making time derivative from here. That is a v prime equal, now in first x derivative 3x squared and x time derivative, so that it can be written in this way: 3x and x prime, because we already know that is 6. So you can put here now 6, and then x is 3, so that 3 times 6, so that is 54. Okay? So of course, if you should add the unit, then that is inch cubed over second. Okay? That's the final answer. Number 4, linearization and differentials. Okay, for the function f(x) equals sec x, and we want to find the linearization at x is minus pi over 4, and we want to approximate the value by using the linearization. Okay, here linearization is given in this way: f at a, but a is now given in this form, and plus f prime at a and x minus a, right? That's the formula for linearization. Okay, so we have to get f prime. Of course, here now f of a. Okay, first we'll try to get f of a. Now in this case, f and minus pi over 4. But that is here sec x, so that is sec and minus pi over 4. Right? So that is 1 over cosine pi over 4. Cosine pi over 4 is 1 over square root of 2, and its reciprocal is square root of 2. So the point is, now fa is given in this way. Now here we have to find f prime at minus pi over 2. Okay, f prime. First we are making derivative for sec x, then that is a sec x times tangent of x. Right? Okay, if we try to write down this one a little bit better way, or you can get here now easily, that is sec x. Okay, so in fact we have to get here now f prime at minus pi over 4. Already we know that the value is same as here now the value and square root of 2, right? And now tangent and minus pi over 4, that will be minus 1, so that it is a minus square root of 2. Right? Okay. Now, okay, we got every value here now. So L of x is the same as f at minus pi over 4, which is square root of 2. And here f prime at a is minus square root of 2. And here now x minus a, so the plus pi over 4. Okay, okay, that is linearization. Now here we are approximating the value f minus pi over 4 plus 0.1, which can be approximated by using here now f and minus pi over 4. Oops, rather than f, we are using L. Okay, here L and minus pi over 4 plus 0.1. Then this is same as square root of 2 minus square root of 2, and x is minus pi of 2 plus 0.1 and plus pi of 2, so that it'll be cancelled out. The remaining part is 0.1. So that is same as now, okay, square root of 2 is common and 1 minus 0.1, so that eventually there's a 0.9 times square root of 2. Okay, that's the final answer. Okay, let's go to number 5. Okay, here we want to find the absolute maximum and minimum for the function on the given interval. In order to do that, you have to find the critical points, and now at critical points you have to measure the value, so that edge point and critical point you measure the values, and among them largest one will be the absolute maximum, and smallest one will be the absolute minimum. Okay, so your edge points are 0 and 4, and we have to find the critical points. Okay, to do that, start with f prime. That is 1 over x plus 1 from this part, and that part is 1/2. If it is 0, that means that x plus 1 must be same as 2. That implies here x is 1. So at 1, we have critical point. Now, you have to measure at the 3 times, and the x's are here now, the end points, 0, and critical point, and right end point. Okay, we have to measure the value, 3 points. So f at 0, which is same as now logarithm, and 0 plus 1 minus 0, which is 0. Okay, f of 1, that is same as now here logarithm 2 minus half, and logarithm, okay, f of 4, which is same as logarithm 4, okay, 5, and minus, and that is 2. Looks like that is a negative, that is positive. So that, and here that is 0, so that the maximum, that one will be maximum, and absolute maximum, and this is negative, so that there will be absolute minimum. Okay, let's check it by using the computer. Here I implemented it, so that is now, and we are making the linear space, and from 0 to 4, 20 points, so that x will save now 20 points between 0 and 4, and uniformly distributed. And along with that, here, now we want to make a plot, and x and logarithm x plus 1 minus x over 2, so that if we hit here, then you can see in this way. So at the 0, that is 0 on the boundary. At 1, we have a maximum value, an absolute maximum. And at 4, that is a negative value here. So that is absolute minimum. Okay. Now number 3. Okay, here we define the arithmetic mean of 2 numbers, a and b, is the number a plus b over 2. Now, we want to show that the value c in the conclusion of a mean value theorem for fx equal x squared on any interval a, b is the same as c here, the arithmetic average of the boundary points. Okay, let's see that. Here, fx is x squared. But anyway, the mean value theorem is here given in this way. For any interval ab, then there is fb minus f of a divided by b minus a is the same as here f prime at c. C must be here between a and b. Okay, so that is the mean value theorem. We want to check that C, once it is satisfied, then C is the here arithmetic average of A and B. Okay. Now, from this one, and that is same as f of b is b squared, and f of a is a squared. Now, that is b minus a. That is same as b minus a and b plus a, and that is now b minus a, so that is now the mid part is a plus b. Right? Now, what is f prime? F prime is f is x squared, so that there's 2x. From this one, here f prime at c is same as 2c. If we equalize that, then we have here a plus b equal 2c, so that we can conclude here c equal a plus b over 2. Ha! We proved that. Okay? So start with left term of the mean value theorem, and here the right term, and you set them the same. Then you can solve for C to reach at here a plus b over 2. Okay. Number 7. Okay. We want to determine the values of a and b, so that f of x equal ax squared plus bx has an absolute maximum at the point 1, 2. Okay. And that means that, first of all, okay, has absolute maximum is quadratic equation, and absolute maximum at 1 and 2 means that, first of all, f1 is 2. And then f prime 1 is 0, because once at 1 it has absolute maximum, then now at the point the derivative must be 0. Right? So we have two equations, and try to get the specific equations for that. Here f1, that is same as a plus b from the definition. X is 1, then there's a plus b, which is now 2. Okay, now what is f prime? That is same as 2ax plus b. From here, f prime at 1 equal same as 2a plus b. Okay, must be 0. So we have two equations for two variables, a and b. Okay, we rewrite here those equations. A plus b equal 2, and 2a plus b equals 0. Okay, we have to solve this system of equations. Just simply subtraction will give you minus a, on the right side is 2. So we have a equal minus 2. Once a is minus 2, then you can easily see that b must be 4. So that's the final answer. Now number n. Suppose that the derivative of a function is given in this way. F is not given, just its derivative is given in this way. Now, at what points, if any, does the graph of f have a local minimum, local maximum, or point of inflection. Okay, first of all, right now here y prime is given in this way, x minus 3 squared. So if you set it 0, then from here you can get here now x equal 0 and 3. That means that here at x and 0 and 3, and possibly local extrema can happen. Now, and to find the point of inflection, you need the second derivative. Okay, so let's try to here now expand this one. So x squared times x, so that x cubed minus 6x and 6x squared plus 9 plus 9x. Okay, so here y double prime is same as 3x squared minus 12x and plus 9. We can get 3 out, then x squared minus 4x plus 3, so that it can be separated out xx and 1 and 3 minus minus, right? And that means that y double prime is same as 3 times x minus 1 and now x minus 3. Okay, so if it is 0, then we can get here x equal 1 and 3. For that points, the function may have point of inflection. Okay, so here by using table, let's check the behavior of a function. Okay, this is x value, the smallest one. Here specific point is 0, and next one is 1, and next one is 3. And then for this point, and now, oops, okay, okay, I have to get pen a better way. Okay, here now. So for f prime, okay, f prime, if x is now smaller than 0, then it's negative. X minus 3 is always non-negative. The x minus 3 squared is non-negative. And then now once x is smaller than 0, the value must be negative. X is larger than 0, then must be positive. So that here that must be negative. And here this is 0 and positive, positive. And at 3, it can be 0, but between 1 and 3, this is positive and again positive. Now how about f double prime? Okay, f double prime. Okay, that is at 1 and 3, the value is 0. Okay, 1 and 3, f double prime is 0. But once less than 1, then it's positive. So that area here now, that is positive, positive, positive. Between 1 and 3, that is negative. And if it is larger than 3, then again, that is positive. So out of this one, behavior of f can be made in this way. Is x is less than 0, then it's going down. But concave upway, down and concave upway. And between 0 and 1 is up and concave upway, like that. Between 1 and 3 is up but concave downway. And between, in fact, larger than 3, then is up and concave upway, right? Okay. Now, at 1 and 3, concavity changes, so that at 1 and 3, we have here a point of inflection, so inflection point. Now, here is going down and up, so that roughly you can imagine in this way. Here is going down, but up here, and now concave down A, again up, concave up A in this way, so that here now the absolute minimum is happening here at x0, so that absolute minimum, in fact this is a local minimum, but eventually it will be absolute minimum at x equal 0. And for local maximum, there's no point which makes local maximum, because the other direction is continuously increasing. Okay, so that's the end of the review. Thank you.